Welcome back to The Explainer. Grab your gear because today we're embarking on a totally different kind of safari, one right into the wild foundational landscape of mathematics. We're opening up the Geometry Field Guide. You know, our subject today is quite literally everywhere. It holds up our bridges, it dictates our architecture, and it's the absolute bedrock of digital graphics. But to really appreciate it, we need to observe it closely, understand its internal laws, and, well, decode its secrets.
It sounds almost impossible, doesn't it? But what if I told you the strongest, most complex structures in the universe are forged from just 3 simple lines? No crazy curves, no infinite angles, just 3 interconnected segments working in perfect harmony. That's the magic of the triangle. So instead of going through a boring old agenda today, let's just plunge right into the mystery.
Section 1. Anatomy of a triangle.
Okay, so every good field guide starts with understanding the basic physical makeup of the creature we're studying, right? Here we have a polygon forged from exactly 3 essential building blocks. First up, notice the 3 vertices, points R, A, and M. Think of these as your anchor points. Connecting them are the sides, or the structural walls, segments RA, AM, and MR. And finally, trapped inside those walls are the 3 angles, the interior joints that give the triangle its distinct posture. And hey, notice that naming rule at the bottom? We identify this specific subject by its anchor points, so we'd call it triangle RAM.
Section 2. Classifying triangle species.
Now that we know what a triangle is actually made of, we quickly realize they don't all look the same. Out in the wild, they come in vastly different shapes and sizes. So how do we make sense of them? Well, just like you might categorize a bird by its beak and its feathers, we classify triangles in 2 distinct ways. By looking at their sides and by looking at their angles, like right, acute, and obtuse.
Let's quickly lock in those side-based definitions before we go any further. An equilateral triangle, it's perfectly balanced with 3 equal sides. An isosceles triangle has 2 equal sides, standing tall and symmetrical. And the scaling triangle? That's kind of the wild card of the bunch, with absolutely 0 equal sides.
Welcome to the taxonomy matrix. When we combine these 2 classification methods, we see that every single triangle actually possesses dual traits. Take a look at that first example, triangle RDB. Because all its interior angles are under 90 degrees, it's acute. But because it has 2 equal sides, it's also isosceles, so its full scientific name is an acute isosceles triangle. Over on the right, triangle CDL boasts a perfect 90-degree corner alongside 2 equal 21-centimeter walls, making it an isosceles right triangle. Make sense?
So a crucial part of understanding any shape is understanding its physical boundaries. Imagine actually breaking apart those structural walls we just talked about and laying them completely flat on the ground. That total continuous distance around the outside, that's called the perimeter. Here, we've got an equilateral triangle with sides of 19 inches. If you trace that boundary and just unfold it into a straight line, it's simple addition. 19 plus 19 plus 19 gives us a total footprint of 57 inches.
Section 3. Internal laws and limits.
We've seen the outside, we've classified the species, but now we have to discover the unbreakable physics of our guide. Behold the ultimate internal limit, the triangle angle sum theorem. No matter how wildly you stretch, skew, or squash this shape, its interior angles are locked to a strict internal law. They will absolutely, invariably, always add up to exactly 180 degrees. Seriously, if you take those 3 colored corners and line them up perfectly along a protractor, they will form a flat 180-degree line every single time.
And this unbreakable law gives us a fantastic survival tool. If you encounter a triangle in the wild and one of its angles is hidden or missing, you can easily track it down using this 3-step guide. Step 1, combine the knowns. Step 2, apply that 180-degree limit. Step 3, find the difference. Let's see this in action, shall we?
Let's step into the computation workshop and see how this builds our understanding. We have triangle BOM here. We know 2 of the angles, 39 degrees and 23 degrees. But angle B? That's a mystery. So step 1, combine what we know. 39 plus 23 equals 62. Now think of the triangle's capacity like a bucket that can hold a strict maximum of 180 degrees. We've already filled 62 degrees of it. Steps 2 and 3, apply the limit and find the difference. 180 minus 62 reveals that our missing piece is exactly 118 degrees. And hey, because 118 degrees is far greater than 90, we can accurately classify triangle BOM as an obtuse triangle.
Section 4. The mirror world of congruence.
Incredible work so far. Now we're entering the final and probably the most fascinating territory of our field guide. But before we go spotting perfect clones, we've got to clear up a pretty massive misconception. In math, you're probably super used to the equal sign, but equality and congruency, they are not the same beast. Equality basically just means two things have the same measurement or value. Congruency, which gets that cool equal sign topped with a squiggly line, demands that two figures have the exact same shape and the exact same measurement.
This visual diagnostic check really hits the nail on the head. On the left, we have equality. It's like balancing numbers on a scale. A 15-centimeter block perfectly balances another 15-centimeter block. They're equal in value. But look over to the right. Congruency is physical. It's about taking two distinct neon triangles and being able to perfectly stack them on top of one another so they physically merge into one.
To truly declare two geometric figures congruent, they have to be perfect clones. Imagine a mirror placed directly between them. They have to check three absolutely crucial boxes. They must be the exact same shape, they must be the exact same size, and every single corresponding side and angle must be completely identical. If triangle ABC looks into that mirror, it sees triangle A', B', C' looking right back, matching identically, piece by piece. Now, because of this piece-by-piece matching, the way we name congruent triangles acts as a highly precise treasure map. It's almost like a secret cipher. This is the matching rule. Look at the statement. Triangle CSD is congruent to triangle KVO. The order of these letters is definitely not random. It tells you exactly who perfectly mirrors who. The first letter C matches the first letter K. S matches V. D matches O. You literally cannot just scramble the letters. You have to map out the corresponding vertices perfectly.
Which brings us to the ultimate prize, the magic key of our mirror world, CPCTC. It stands for corresponding parts of congruent triangles are congruent. I know, it sounds like a mouthful, but the rule is incredibly simple and hugely powerful. Once you prove two triangles are twins, this magic key logically guarantees that every single matching angle and side is also a perfect twin. It basically unlocks everything you need to know about the clone shape.
To really master this mirror world, just remember two absolute properties. First, the reflexive property. If a shape looks directly into a mirror, it is always congruent to itself. Triangle XYZ is congruent to triangle XYZ. Simple enough. Second, the symmetric property. The mirror is a two-way street. If shape 1 is a perfect clone of shape 2, then shape 2 is unquestionably a perfect clone of shape 1.
Section 5. Field Test Knowledge Check.
All right, explorers, we've mapped the anatomy, classified the species, discovered the 180-degree internal law, and navigated the mirror world of congruence. It's time for a survival test. I'm going to read these out, and I want you to mentally lock in your answers as we go. Ready? Question 1. Find the perimeter of triangle BOM with sides measuring 11 centimeters, 8 centimeters, and 5 centimeters. Question 2. Classify triangle HAF by its sides if all sides are equal and side HA is 34 centimeters. Question 3. If triangle ZYN is congruent to triangle SAB, which angle perfectly matches angle Z? Question 4. Following that exact same logic, which side perfectly corresponds to side ZY? And finally, question 5. True or false? The congruency symbol means exactly the same thing as the equality symbol.
Take a second. Think back to the perimeter boundary, the species matrix, those precise letter maps, and the balancing scale versus the perfect clones. Do you have your answer securely locked in? Let's reveal the truth of the field.
Let's see how you did. For number 1, unfolding the boundary means adding 11, 8, and 5 to get a perimeter of 24 centimeters. For number 2, if all three sides share the same measurement, it is fundamentally an equilateral triangle. For number 3, using our precise cipher map, Z is the first letter of the first triangle, so it matches S, the first letter of the second. Same for number 4. Side ZY corresponds exactly to side SA based on that vertex order. And finally, number 5 is a resounding false. Equality is just about measurement. Congruence demands identical shape and measurement. If you nail these, you are officially a geometry survivor.
We've reached the end of our expedition for today, but honestly, your journey is just beginning. You see, geometry isn't just something trapped on a chalkboard or a screen. It's the physical blueprint of our reality. So I'll leave you with this final thought. Just look around your room right now. Look at your ceiling, your furniture, the architecture right outside your window. Where can you spot the hidden triangles holding up your world? Once you actually learn to see them, you realize we're surrounded by these incredible three-sided wonders every single day. Thanks for exploring with me, and definitely keep your eyes open for the geometry all around you.